Okay, good afternoon to all the juniors, and welcome to third period. Who missed all the third period will be watching this lecture tonight. So say hi, third period. Hi, third period. Yeah, so they were doing junior career at that time. So what we're doing today, up here I wrote on to the left of the board, there's a list of by the end of Unit 12, you guys are going to be able to find the pH of all 5 of these things: strong acids and bases, weak acids and bases, salt solutions, buffer solutions, and what I call invader problems, which are taking any of these two and mixing two of any of these and mixing them up, and how to find the pH of pretty much anything. So yesterday we did the pH of strong acids and bases. So how do we find the pH of a strong acid and base? What did we do? We did what? Negative log of, if it was pH, we did the negative log of the H plus concentration. But what did we make the assumption of? If we had an acid that was 0.5 molar and it was a strong acid, what did we assume? Dissociation was 100%, so the concentration of the acid would be equal to this concentration of H plus. So that's for strong stuff, and that was yesterday. Today we're going to look at how to find pH of weak acids and bases, and we get to use rice tables. So this is easy. You've done it now with rice tables. You're going to know how to do it. And how do we know we need to use a rice table anytime it's not strong? You've got to use a rice table. End of story. So let's start this. Calculate the magnitude of the equilibrium constant for benzoic acid if 0.1 molar solution has a pH of 2.5. So they're asking us to calculate the equilibrium constant. Since we're finding the equilibrium constant of an acid, just get used to seeing it as a K with a lowercase a. We're looking for Ka. But it's the same K we've been finding, products over reactants, no problem. So anytime you start a rice table for an acid or base, I want you to follow these steps. I don't care what the textbook says. The textbook doesn't have you add water all the time, but it makes your life so much easier because there's points you have to add water. So always take your weak acid or base, if it's a base, and add it to water in your rice table. So you get H, C7, H5, O2. I want you to add it to water. Water's a liquid, so that goes out. We're in equilibrium with, now, this is an acid, so it's a proton donor. So it's going to donate, and we get two products, C7, H5, O2 to the -1, plus what? The hydronium ion, which is the same as H plus. Okay. It says calculate K. So if we need K, do you agree we need all these equilibrium concentrations, right? So what do we know? They gave us, it's a 0.1 molar solution. That's your initial concentration of your acid. So before it has a chance to do any dissociation, how much do I have of the products? 0. Which way do we have to shift to get to equilibrium? -X plus X. What you're really going to like about acid-base, because we're just transferring one proton, all our coefficients and all our problems are going to be 1. So we're not going to be raising stuff to the power of anything. It's kind of cool. So it's going to be a little bit easier. The math is going to be much easier. 0.1 minus X, X, and X. But if I need to find Ka, I need to know what X is in order to plug it in to get those concentrations. There is another piece of information they gave me. What was that? They told me that the pH is equal to 2.59. Any ideas? I can find, knowing pH, I could find the concentration of the H plus. Remember, pH is equal to negative log of H3O plus or H plus. Okay? So all we have to do is 10 to the negative 2.59, and that will give me X. So someone do that for me, please. Okay, so we get 0.00. We went ahead and just left 2 sig figs because we have 2 decimal places in our pH. So that's 0.0026. So that's equal to our X. So we know that this is 0.0026. And what's 0.1 minus that? 0.097. Okay, now we're pretty much ready. I'm going to write my unsubstituted equation. Ka is equal to C7. This is the equilibrium expression. -1 times H3O plus. Since the water is a liquid, we don't include it. We just put it over the full-blown acid. And I can plug in, and I get 0.0026 squared. Oh, it's wigging out on me. There it goes. 0.0026 squared divided by 0.097. And what do we get? 266. Times 10 to the 5th? -5th, okay. Now you see how I was like 10 to the 5th, really? Why would I be like 10 to the 5th? Any ideas? It's KAs and KBs for bases are supposed to be small because they don't dissociate very much. It's a small percent. Okay, so when I saw a big number like that, I was like, something's wrong. So our Ks will be smaller compared to the Ks we've seen before. Got it? So what's favored? The forward or reverse reaction? Reverse reaction. We're going to have more actual acid than ions in solution. All right, let's do another one. I'm going to introduce another idea to you. It says calculate the magnitude of the equilibrium constant for, again, we're calculating the K. I want to calculate pH. We'll do this one. We might add on a couple more problems. So again, we're looking for the K, but this time we have a solution of ammonia. So what kind of K are we solving for? A KB. So just like before, you're going to take your ammonia and you're going to add it to water. Okay. And this is a base, so the base is actually a proton acceptor, so that's going to accept a proton, and it's going to make ammonium plus OH minus. We're not even going to put this in the chart. Our original concentration is 0.1. This is 0. This is 0. Minus X plus X plus X. We get 0.1 minus X, X, and X. They told us that the pHs, this is a little bit different. It's not harder, but if we do 10 to the negative that, what do we get? H plus, but what do we need? Concentration of OH. So I'm going to go ahead and get POH from this. How do I do that? Good. So what do I get when I 14 minus 11.3? Give me 2 decimal places. 2.87. That's my POH. So now if I go 10 to the negative 2.87, that'll give me my OH concentration, which is 0.0013 moles per liter. So that's what I can put in there. See what I did there? How seamless that was? It's pretty amazing. All right. So we get 0.0013, 0.0013, it's wigging out again. And then our NH3 concentration after equilibrium, 0.099. All right, so if I write my KB, that's equal to ammonium times the hydroxide divided by ammonia. That gives me 0.0013 squared divided by 0.099. So what's my KB equal to? So what is it, KB? All right. Okay, let's go on to our next problem. This is supposedly our last problem, but I think I might add on another one just for practice. Here we have, we're told now, this is the point, calculating the pH of these acids and bases. This is a methylamine. Does anybody remember from yesterday what a methylamine is? a base, a nitrogenous base. That's the point. So how do I know this is a base? Because I told you the amines are bases, and you can also, there's something else out there that's telling you it's a base. KB. Okay. The reason you need to know that is because when you do your rice table, you got to know whether it's donating or accepting a proton. So we're going to do a rice table here. We're going to take our base and do what to it? Add water. So the base is a proton acceptor, so now we just chunk it on the hind end into the additional spot on the nitrogen. Gives it a positive charge, plus OH minus. Our original concentration, then, is 0.712. Water is a pure liquid. We don't even include it. At the beginning, we've got no initial concentrations of these guys. We know KB, we're looking for pH. Minus X plus X plus X, 0.7, let me rewrite that, 0.712 minus X, X and X. Now if I'm looking for pH, how is this table going to help me? Find X. What is X? This is what, right, that's the concentration of OH. Once I know that, I can get the POH and then pH, okay? So I'm solving for X here. Now, here's where acids and bases are awesome. Here, it's the Donald Trump factor. Because our Ks are so small, and because these weak acids and bases break up so very little actually leaves and becomes ions, very little dissociates, usually, and we're going to show a mathematical justification of this, we could drop this X, okay? I call it Donald Trump because I look at this guy right here as if he's Donald Trump. If Donald Trump drops a dollar bill on the side of the road, does it change his overall fortune? No. So we can mathematically just ignore it. Here we can't ignore it because these guys got nothing. They're like the bums on the side of the street looking for the handout. That makes a difference to their fortune. If they make $5, they're really happy. So we're going to keep those X's, but we can drop this X initially, do the math, and then we might have to go back and put it back in depending upon the situation, and I'll talk about that in a minute. But for now, we're going to go ahead and drop that X. Let me just really quickly write my expression. But what it does, it keeps you from having to use the stupid quadratic formula. It's awesome. KB is equal to blah, blah, blah. So we know KB from above is 4.4 times 10 to the negative fourth is equal. We're going to have X squared, but we're just going to put it over 0.712 because we trumped it, as I say. So there we go. We don't have any quadratic formula to contend with. Go ahead and give me X to 366, please. Well, 2 technically because you're K. So K is 266. What is X? 3.1 times 10 to the negative fourth. This is moles per liter. No, it's not right. Okay. Oh, so, okay, I'll leave it up there. So we want square root. No. X squared is equal to that. Okay. It's not my fault, home audience. I've got to teach my kids some calculator skills. So this was, tell me this again, 3 point, and then we take the square root of it, we get 0.018. So that is my concentration, moles per liter, of my OH. So if I take the negative log of OH, I get POH, right? So what's a negative log of 0.018? 1.75, that's POH, but is that what they're asking for? No, they want pH, so 14 minus that gives me a 12.25, which is 266, so this is correct. And it makes sense. I want you to stop and think. The pH scale says bases are below or above 7. Above 7, so that's what the pH scale is telling us. If you stop here, by accident and you do that check, you'll realize, oh, I can't have a weak base with a pH of 1.75, so that can't be right. Does everyone get the Donald Trump? Okay. Okay, so I'm just going to throw in one practice problem. I'm going to set you up. I want you to work it. I'll turn the video off. And then once we get the right answer, I'll turn the video back on. So this is a try yourself kind of problem. We have an acetic acid solution. And I want to know what the pH is for a 0.25 molar acetic acid. I've given you the K right there. So go ahead and get her done. And I will be writing while you're writing, so don't look up. Go into it. So you add your acetic acid to water. Acid's a proton donor, so we get C2H3O2 minus plus H3O plus. We have an original concentration of 0.25 minus X plus X plus X. We're going to trump it, and I forgot on the last problem to show you how to justify the trumping because you have to justify it. So I'll do it in this problem. But we get X squared over 0.25 is equal to our Ka of 1.8 times 10 to the negative fifth. I didn't write my expression. That's okay for now. So X is equal to, what'd y'all get? 0.0014? No? Okay, I need it, somebody. So we have a correction. It's 0.0021 moles per liter. That's going to be equal to our H plus concentration. So if I take the negative log of 0.0021 to 2 sig figs, meaning 2 decimal places, the pH is 2.68. And that's acidic, and that makes sense. So this is acetic acid. Now, one thing I failed to mention in the last problem, and we'll go back to it. If you decide to trump this, you have to say it's negligible. Is it gibble or jable? You have to say it's negligible, and the way you actually mathematically prove it's negligible is to calculate something we call percent dissociation. So I'm going to go ahead and do this to the side. What percent dissociation is how much dissociated. Duh. Okay, so you take how much actually left the acid over the total concentration of the acid. What on the table represents how much left the acid, how much dissociated? X, right. So what you do is you take the X that you calculated, which we found out to be right here, this is X, 0.0021, and put it over the original concentration of 0.25, part over whole, times 100, and you're going to get a percent. What is that percent? 0.84%. 0.84%. Yeah, that's small. It's a 5% rule. If your percent dissociation is above 5, you need to go back, put it in, and use the quadratic formula. Okay? Here, the percent dissociation is less than 5%, so it was okay to drop. And that proves the mathematical negligibility of the X. Okay? We didn't need it. It only dissociated 0.84%. So let's go back to that previous problem and do the percent dissociation, because I was a slacker. I didn't do that with you. And I also don't have a whole heck of a lot of room either. So our percent dissociation is our, again, you have to say this is negligible. And to prove the negligibility, we're going to take part, which is X. Our X came out to be 0.018 over the original concentration, of 0.712 times 100. And what is our percent? 2.53%. Okay, is that less than 5? Yeah, so we're good. We don't have to re-include the X. A lot of times they'll just ask you for a separate percent dissociation calculation. And sometimes they'll say justify the drop. All right, das ist alles.